Okay, so I'd like to introduce Wesley now, and he's going to talk about Team Miles, CubeQuest Deep Space Mission by citizen inventors.
Hey everyone. So thanks for having me. First off, I should emphasize that I am a citizen inventor. I'm not I'm an aerospace engineer. I'm not even a scientist by training. I'm typically an industrial engineer by training, and that's pretty typical of the people I work with at Team Miles. And we're here to share our experience, maybe coming at your world a little differently, and hoping that maybe some of the trade studies and the thought processes that we had to go through will shed some light for you, maybe accelerate some things for you, and make your projects better and more interesting. Okay, so I don't actually have a slide. I apologize to my team members who are going to watch this later. I don't have a slide that has everybody who has ever participated in our team. There are several people not shown on here who have made very lasting, meaningful contributions to the project. But interestingly, among here, to understand our team, you've got, say, myself and Frank. We both served on the part-time scientists, the Berlin-based Google Lunar X Prize team, who are now launching things to the moon shortly. We went as far as Americans could go under ITAR, contributing. There are certain things where I can act as a manager and encourage and coach, but I can't actually do for those people. Now, subsequently after leaving, some of those things have been removed from the ITAR munitions list, subject only to export restrictions. But Frank and I did all we could and had to back off, but we've been part of a space dream before. Don and I, we invented a small plasma thruster. Bald spot shows a midlife crisis that happened during that process. And, the bank account shows we bought a CubeSat kit from Interorbital and sort of set ourselves to self-induced college to get involved in the space industry rather than buying red sports cars. And then you have Sydney, who is the only one on our team who was a degreed aerospace engineer, who went back to that after being a software developer for most of her life, said, you know, I'd like to actually do something with flames and science. We've got a couple of degreed artists, full-time artists, sculptors, artists on board, a variety of other skill sets. Charles is interesting. He actually does work with ceiling fans and is a prolific inventor, prolific patenter. So Seth has a degree in finance, but after having watched engineers work equations, that to him looks like Harry Potter spells. He's gone back to school, getting a graduate degree in engineering, because he would like to be able to cast some of the spells that you and I take for granted. So we have a hodgepodge, maybe not your normal team, and that really affected a lot of our decisions. We joined the CubeQuest contest. I joined it because Don and I invented this thruster, which was really an age-old passion for the longer story. And NASA said at the first CubeQuest summit, they said, we want the unusual ideas. This is a good way to get your unusual ideas heard by the experts and get some peer review. So I had figured there'd be 50 to 70 teams joining CubeQuest to keep the door down just to show their gizmo to NASA and get on the radar. And so that's what got me into it. Seth, on our team, he and I went to the same hackerspace in Tampa, because there are hackerspaces and makerspaces here. We actually met each other at the summit. So I didn't know you were interested, I didn't know you were interested. And so we started getting together on the team. And so when this ragtag group, which started to snowball, more and more people started to get together, the first thing we said for the first ground tournament, that's GT Ground Tournament 1, is we said, do we want to be part of ground tournaments, or do we want to just try to buy our own ride and not compete for a ride at CubeQuest? We said, kind of idiots about this. We have to compete for a ride. Nobody's going to fund us money to buy our own ride. We have to compete for a ride. And more than that, we're volunteers, and we need to force the metronome of ground tournaments, to force us to focus, concentrate, and avoid analysis paralysis. frankly, coming at it from my side, I see a lot of aerospace projects that enjoy analysis paralysis because paychecks are attached to them. We have no paychecks attached to us. We have to keep moving. So that is perhaps a difference than you might have for some of the studies you do. So the first thing we did is I set off trying to find a trajectory. Can we even do this mission with the gizmos we want to show in NASA space, thrusters? And the rest of the team went off and played fantasy football. They played fantasy satellites with cubesat.com, Cloud Space, Blue Canyon, anybody else selling gizmos on the internet. And they started to build satellite designs from those gizmos to see what was possible and to highlight really our ignorance and what we needed to learn. So we ended up with selecting a polar lunar orbit. We decided we would get kicked off of EM1 inside the Van Allen radiation belts. That was the only way we could hit the brakes hard enough, long enough to actually get a lunar orbit. We decided we did not want to do a reach stability boundary. We wanted a nice short 5-day trip. So we did not have a differential equation background. We were comfortable with a 200-day reach stability boundary trip. We wanted to be sort of short and simple. So that led us to this highly elliptic polar orbit, which turned out to be Earth synchronous, which is a wonderful orbit because now you can camp your satellite to the side and have near continuous views of any ground station on Earth 24/7. So Earth synchronous polar orbit was wonderful. And then towards the end, we kick on the thrusters and we slingshot past the moons. We do a little gravity assist. So that's entering orbit. We get a gravity assist and we leave. And we found, actually quite by accident, this charming orbit which takes us most of the way towards Mars orbit. Never close to Mars itself, but about half the way to Mars orbit. And we said, all right, it's possible with our gizmos. What happened with the build? And we assembled all the knowledge we had from our builds, the fantasy football, if money were not an option, what kind of parts are available. And we came up with this satellite design here. So a 6U box with fixed solar panels that of course have to be flat inside the deployer. They come up to 45 degrees. They come up to fixed 45 degrees because the satellite is bobbing and weaving all throughout this trajectory. Earth synchronous orbit means you don't have a steady face towards the sun. And so 45 degrees turned out to be the best average mission power. And we said we can't articulate these things. I see a lot of designs for articulation. This is a contest we were joining. The rules of the contest said you lose 20% of your score automatically if you have any moving parts. So we don't want to lose 20% of our score automatically, just get a little more solar power. Can't we just design the system to use a little less power? So these are the things driving us that maybe not drive you, but maybe could. Maybe you can find inspiration in that. So we divided our spacecraft into this big 1x3 column that's our invented gizmo. That's our thrusters and our propellant tank, one giant conformal tank with big fingers that reach down to all the thrusters, 14 thrusters on the back side of it. And then over on this side, you've got the COTS side. So you've got a couple of star trackers, you've got 3 power supplies, you've got some of our team members who are inventing, but from our perspective, COTS, a new kind of computer, the blending of COTS and rad-hard computing that is going to drive it all. We've got our off-the-shelf communication system, 4 sun sensors. You see we're using iodine propellant, and then the big spine of 18 batteries down the center of the craft, situated at the point where charging and discharging them, the heat from that helps keep our propellant tank warm, but also they can capture waste heat from the computing system to keep the batteries themselves warm. That was our take on it. The overall why, just sum it up, money and time. Okay? We don't have a lot of money, we're volunteers, we don't have a lot of time. Like for instance, we're not RF engineers. So we said, what is a link budget that we know works? What did Laddie do? How many watts did Laddie have? What was their gain? Roughly how could we make that work? So we picked transmitters, we picked a power budget that fit with NASA's published missions of this worked. And why it worked, that still took some education on our part. Okay? I'm probably shy about that. It still took some time to learn why that worked. But we know if we were to emulate that in the budget, we had a good shot at making this work. Likewise, we're not made of money, and communication resources on Earth are very, very expensive. So we said, look, this thing has to be highly autonomous. Not because we don't want to drive it around, but we aren't available for ground mission, because we can't afford to buy the communication assets. So we've got to be very, very autonomous. Because it has to be very autonomous, it has to be very radiation resistant, especially because we have to get off inside the Van Allen belts. We have to be active and running during the Van Allen belts. 5 minutes? Wow, okay. So we'll speed up this. Upshot is, we got first place in ground tournament 1 with this approach. We stood out. We came out strong with a strong vision. Ground tournament 2, we made further changes. We kept refining things. We added a Faraday cage. We added some ground separation because we're flying into our own exhaust plume. So we're self-charging the spacecraft because we're putting on the brakes. Instead of accelerating, we're putting on the brakes. So we're self-charging. So we added some things to deal with there. We further simplified things here. We got better at our rendering. See our Faraday cage. We actually did some thruster testing. We actually lost that Charles guy from the project as soon as we started doing the thruster testing, because the fan company we worked for started doing the plasma, and they didn't want any semblance of those patents crisscrossing, so we actually lost somebody for that. So we turned in 1,200 pages of design detail on this, and we dropped to spot 5, which is still good. Still good, same money as first, but it was a real punch in the gut, okay? So that elaboration actually kind of hurt us, mainly because we're software engineers. Anybody know the fable, the cop wears shoes? Who has the worst shoes in town? The guy who repairs shoes. He's always worried about somebody else's shoes. Those 1,200 pages we turned in had very little to do with the autonomous software. For us software engineers, well, engineers by training, software engineers by paycheck, the software was the most natural thing. But for the judges, it was the most weird thing. And so, not understanding our audience, we neglected to talk to them. And that's when we made a major design choice. We said, what is our real goal here? Is our goal to go to the moon? Is our goal to write autonomous software? Or is our goal to demonstrate Gizmo to NASA, which we think did fairly well been accomplished? We received some feedback and got going on there. Or is our goal to do well in the contest? We said the goal is to do well in the contest, and literally a few of us cried at it, but we said goodbye moon, hello deep space. We came up with an idea that if you have good knowledge of where the sun is, and good knowledge of solar north, which you get from your star trackers, a simple cross product, like you can do on an Arduino 8-bit processor, a simple cross product is all you need. And you can tell you have 2 poses. One pose where you swim in the plane of the ecliptic. With the thrusters on, you will raise your orbit that way. And another pose where you point the craft north, we call this the ballerina pose, and the ballerina twirls the antennas on their side. As the antennas twirl around, their beam cones sweep past the Earth. You no longer need to know where is the Earth. You just point north, you do a few turns, Earth will have received it somehow. That's all you need to know. And you go back to swimming, and you raise the orbit. Orbit raising was deemed important because orbit raising gets us farther, faster than our competitor, who is also going for the same prize. Now, this simplified mission plan is exceptionally robust. I don't have time to go through this chart, but you could be off by 45 degrees and still accomplish the mission. So the pointing error people fuss about, no longer a worry for us. Okay? It's phenomenally efficient. Likewise, we made a bunch of changes. Since knowing where the sun is very important, we moved up to 6 sun sensors instead of 4. We had commercial orders for the thruster, and looking at the safety needs, we said we can no longer go with a custom arrangement, that this project is the same thing we're offering to the commercial world. In order, that's a cost-saving thing, that's a time-saving, effort-saving item. So we made design changes to the thruster, the tankage here, in order to accommodate what the commercial is coming up with. And notice this large open area right here, room to spare. So we turned to this one in, and we're back in first place. Back in first place in the contest. Now GT4, ground tournament 4, we're still waiting. We'll know next week. But this mission, ground tournament 4, has had a few little changes. So you can see we've got our two-way communication. Notice the solar panels aren't on the body anymore. They're way out here. This is a manufacturing step. This is because, I gotta tell you all, the solar panel manufacturers are really hard to get details out of. Okay? Very hard to get details out of it about exact mounting locations, exact places for hinges, etc. So we had to punt and say, fine, it'll be an add-on instead of a direct thing on the satellite. We have an add-on so we can change vendors at the last moment when we get the details. These are the things we're noticing from the industry side. So we go out to 45, at 45 days, we're at 4 million kilometers, the minimum needed for the farthest communication distance prize, so that's what we're competing for. We still keep that nice orbit, actually a little closer to the Mars orbit, but never very close to Mars itself. We could actually get out past the Mars orbit. We use about half of our propellant to do this, including all the attitude control changes. We actually have to do a checkerboard coating on the spacecraft to soak up as much heat as possible, because we get kind of cold at the end. But we're jet black spacecraft at the end, we're razor temperature. We boil our batteries at the beginning. So we had to strike that balance of lunar temperatures versus near Mars temperatures. One of the things that's a challenge is because when we're transmitting and thrusting, we have a lot of energy leaving the craft that would normally be retained. And so we have actually pretty strong temperature swings of the craft when the thrusters and communications are running at the beginning. Towards the end, the running of communications is fairly small temperature swings. Spacecraft changed a little bit after that. The NASA safety panel, to a 60% of the score, they matter a lot to us. NASA safety panel worries a lot about batteries, so batteries move out of the Faraday cage into a protected, shielded environment just to be safe. And so all this payload space they're hoping to sell off to somebody had to be consumed for the safety's sake. Again, our priority is not to carry payload, our priority is to do well in the contest and to have a gizmo out in space. So we make perhaps different decisions than other people would. This had actually a benefit for attitude control, so I know I'm not going to complain too much about it. We also streamlined the thruster controls, removed the last thing needing real-time operating system on the CPU. So now we're back to just standard COTS operating system is good enough to run the whole thing, and we continue to reduce our manufacturing costs. Thermals, people mention that a lot here, so I'm going to share ours. So out towards the Martian orbit, where things are really cold. See, our solar panels are quite cold, but the main craft body actually does pretty darn well. We're showing here the transmission case. You see the radios, they're the hottest, and we still actually need to spread that heat a little better than we've already been doing, so we still have a few more steps to do. And curiously, the black body temperatures we computed early on, they agree with the average. The average body here where the batteries and the tankage are, which are the critical components, most temperature sensitive components on board, those actually agree within a degree of the black body temperatures we've been computing all along. So really pleased with that. And perhaps one thing that's different with us, when we do our attitude control, there's no reaction wheels, moving parts are 20% reduction, we like that. So we've got a dozen thrusters on the back and the canted, so we've got a 3-axis control by activating any of the hundreds of combinations of thrusters available. And so, I wanted to share that does turn out to be viable. We give ourselves 5 minutes for any pointing maneuver, and it turns out that there are hundreds and hundreds of combinations of thrusters that will accomplish any of those maneuvers. So we have actually really good redundancy. But we abandoned the notion of throttling thrusters as a simplification to keep the processor non-real time. So that's a quick tour of how we got here, where we're at. I think it's good.
Wesley. Now we'll take some questions.
So what do you think your budget for building the hardware will be?
For building, pardon?
For building the spacecraft, how much do you think it will cost you?
Well, we're telling investors 600,000, but we have plans for 400 all the way down to 150, with various degrees of redundancy and explaining things to NASA safety.
So the rules of the competition force you to the lowest common denominator. If you kept some delta V back, keep anything else back?
We've got plenty of power margin, and we have pretty good comms margin. And we had a rejected experiment to do a quantum tunneling experiment, and there is technically room in data processing and comms bandwidth to do that. I want to know personally if quantum tunneling rates, if they vary throughout the solar system, because if they do, that would affect, say, enzyme formation and such. It'd be a cool biochemistry experiment after fish.
How challenging has it been to work with NASA to work through their processes and I work for NASA, so it's one of the things we have to do is learn how to work with this community more efficiently. So I was just curious your thoughts on the process.
I've seen a wide spectrum of responses from NASA. I will say that as citizen inventors, we decided we could not possibly learn all of aerospace, so we would rely heavily upon the required outline for the submissions, for the ground terminal submissions, as a syllabus. Go learn this, go learn this. Probably the most unusual thing we've had to deal with is that NASA assumes that we have silos of knowledge. That there is a person or a small collection of people who are dedicated to batteries and another dedicated to computing. In practice, because we're all volunteers and we come from the maker community, the social contract with my friends who joined was, don't make me learn only one thing. I don't know what I want to be when I grow up. Let me try everything. And so we're very organic in how we're organized. That has been a stress with classically trained aerospace engineers when we interface with them. That and I joked about an RTG unit on April Fool's once with a payload manager. I think I caught him on a day with Logan. Don't do that.
Any further questions? No, in that case, let's thank Wesley again.